do some examples of trinomial factoring. I have, how many problems today? I have 12 problems today. So again, I'm going to go rather quickly once I show you a procedure on the first couple. Every time you have something that says factor, the first thing you want to search for is count the terms 1, 2, 3, and see if there's anything common. P squared, 6p, no p's, no numbers common. This does not have a common factor. Then you have to say, well, it's a trinomial, so the question is can I look at the first and last term and come up with something that works? P times p makes p squared, and this is the common thing. So I get this right away. That makes p squared. The question is now, what are the factors of 5? Well, there's only 2, 1 and 5. So is there a way for me to use 1 and 5 and get a positive and a negative sum? Well, 2 negatives, right? And is negative 5p and negative 1p negative 6p? The answer is yes. So my answer is this. If I want to check, I can re-multiply the binomials and come up with the original problem. Every problem can be double checked this way. And you really don't ever have to miss one. On the next one, we come and look. Now, it's only 2 terms, it's not a trinomial. So we look, is there anything common? There's a 2 and an 18, so 2 is common. N squared and n, so an n is common. So just pull out the 2n. And again, check whether distributing 2n against your binomial here creates the product of 2n squared minus 18n. It does, so that's all there is to it. Problem 3 is very much like problem 1. In fact, the only difference is the sign. So again, we can use my chart up here for 5 and 1. It's the only factors of 5. And I can write n and n to make n squared. 5 and 1 are the only factors to the question. So those are the only 2 I can put there. They both have to be positive to make a positive sum. And again, if I multiply the binomials, we'll find that they are equivalent. Problem 4. We look at this and we see 3 terms. 5, 20, and 105. You should catch, because they're all 0, 5s for endings, that 5 factors out. And that's where you have to start. And I really want you to rewrite this. Because now if we got the 5, we can see we have x times x, 21. So I have 5. And the question is, what are the factors of 21? 1 and 21. 3 and 7. Again, I check sums. 1 plus 21 makes 22. 21 minus 1 makes 20. I am looking for 4. I am looking for 4 because we factored out the 5. Well, that means 3 and 7 have to be my partners. I'm looking for a positive 7 and a minus 3. And I can check this by multiplying. And again, I can write it any number of ways because I can multiply in any order. I could rewrite it this way. The x minus 3 binomial could be first. For the sake of space, I'm just going to take this out. It doesn't matter. Number 5, like number 4, has a common factor. We always want to see if that first number is common. And it is. And again, n times n makes n squared. What times what makes 24? How about plus 8? Minus 3 this time if you do the multiplications. Because 8 times negative 3 makes 24. Negative 3n plus 8n makes positive 5n. Again, take a look. First things you have to do is get out the common factor. In this case, it was 5. And now it's a difference of 2 perfect squares. Again, it comes back to this property. A squared minus b squared is equivalent to multiplying the conjugates because the middle term eliminates. So knowing that, I can write 6 as x minus 10 and x plus 10, or x plus 10 times x minus 10. And again, multiply this out to check it. Every time we can do that. Problem 7. And again, problem 7 happens to be exactly the same as problem 1. K times k makes k squared. Negative 5 times negative 1 makes positive 5. Negative 1k and negative 5k make negative 6k when you add them. Difference of two perfect squares. It's a difference. You take a look if the square roots work. They do. K minus 9, k plus 9. Now you're flying along like this and you say, hey, 9's the same. It's not. You got to check the common factor. I haven't been saying that, but every time I look at these, I say, is there something common? In this case, n is common. So I just pull out the n and I'm done. Whereas 10 I look at and there's nothing common. Then I say, hey, it's a difference. Square root of b squared is b. Square root of 36 is 6. So how about we write it the other order, b plus 6 first times b minus 6. Last two, last four, 11, 12, 13, 14. Again, 16 has a lot of factors. 1 and 16, 2 and 8, 4 and 4. I have to make 6. It's going to be 2 and 8 because 8 minus 2 makes 6. M times m makes m squared. I need a minus 16 minus 6, so it's going to be negative 8 plus 2. That is equivalent to the trinomial. We have factored into two factors. You multiply these factors, you'll get that product. Again, 12. You see this? You see, hey, I sure hope 6 comes out. And it does. If you pull 6 out, you get 80. Now with 80, it's a lot harder. You got to think of all those factors. And there's a lot of them. 1 and 80. 2 and 40. 4 and 20. 5 and 16. 8 and 10. And again, we're looking for sums or differences out of these number pairs, okay? Each pair that makes negative 2. 10 minus 8 or 8 minus 10. 8 minus 10 makes negative 2. So, I have 6. X times x makes x squared. Negative 10 plus 8. The sums on the other ones, all right, would be, like this one would be 11 or 21, 24 or 16, and so forth. You can find them. And again, this is a review. You should be able to do some factoring before you watch this example video. Call it the 6 because it's common. Alright? What times what makes 70? 7 and 10. And 10 minus 7 makes 3. So positive 10, 10 minus 7. And we're going there. Finally, positive sum, positive product, n squared, n times n. How about 8 and 3? Again, this is just to help you review trinomial factoring or factoring in general of polynomials.